just going to make a note here, inference. We'll see that as well in one of the examples. So, some terms that we kind of got set up with in our problem set. Beta. Beta is simply the parameter for slope. It's the slope of the population's least squares regression line, the parameter for slope. And alpha, isn't it lovely when something has two meanings in the same curriculum? This is the parameter for the y-intercept. Excuse me. So the line of regression for the population would look like this. Y equals, no y hat, just y, alpha plus beta x. But we don't usually have those values. We have to make inference about them. What we end up with is we have b, which is our statistic for slope. And our a, which is our statistic for the y-intercept. And that's what we find in our line of regression that we have worked with since, I don't know, chapter 3, I think it was. The least squares line of regression. Sometimes you'll see that as LSLR. It's just the line of regression. So when we're dealing with significance, we have to have a hypothesis and an alternative. The hypothesis deals with the line of regression slope. I probably should add something to this. Let's add the real line of regression, meaning that it's the parameter line. It's about the whole population. And if I knew that, I wouldn't have any reason to find anything significant about it. I'd just have the data. So our null hypothesis is going to be about this slope, that the beta equals 0, that there is no slope. The slope of the true line of regression, or the real line of regression, so if beta equals 0, what's the alternative? Exactly. Doesn't equal, or is greater than, or is less than. So remember, when we're testing a hypothesis, we always have to test it against a parameter, like mu or, in this case, beta, something like that, or p was real common. T-value. The t-value is calculated as b, the slope of the least squares line of regression, divided by the standard error of b. Slope of the LSLR divided by the standard error of the slope. And this standard error of b is the sum, the square root of the sum of the residual squared over n minus 2 degrees of freedom, all that divided by the square root of the sum of x minus x bar squared. Again, we live in miraculous times with the calculator helping us out with all that, even if we do have a few steps to do it. Thank you. And degrees of freedom, n minus 2, just like it was the other day. So alpha, beta, hypothesis, beta equals 0. The alternative is that it doesn't equal 0. This t-value thing, I think it'll work itself out for us. So shall we look at a problem? This problem is a little lengthy, but it's good in the sense that it has pretty much everything that I want you to know all in one problem. It's 1511. It's on page 908. Page 908, and guess what this one's about? It's an extinct beast. Apparently the writers in this book really thought a lot about the Archaeopteryx and how they might be able to write questions around it. So this gives us a table from a different program. So I'm just going to write it in here. Hopefully I have enough room. Coefficients. Coefficients. And we have intercept. And femur, bless you, and value, negative 3.6596 and 1.1969, and then it gives us standard error. As 4.4590 and 0.0751, and t-value negative 0.8207. And then I have this last thing. I'm not even sure what this is. PR, parentheses, is greater than the absolute value of t. Close the parentheses, and that is 0.4719. If the teacher says he doesn't know what it is, then it's probably not important. At least it's not going to change my life in any significant way, I don't think. So we have this data, and they want us to use this to work with the rest of it. It says, what is the equation of the least squares regression line? Can we pull that out of this data? Any thoughts, guesses? I agree. Yeah, that would be the slope. Yes, good. So we've got slope and y-intercept. So y hat equals negative 3.6596 plus 1.1969 x. That would be the equation as it should be written. B says we left out the t statistic for testing the null that beta equals 0 and its p-value. Use the output to find t. Well, t equals b over SE of b. And fortunately, we have those numbers. The b is the 1.1969. Standard error of b. What's that? It is. That's good. It is the 0.0751. So that would be a correct interpretation. Good. And so we divide those two, and we should get a number that's pretty large in terms of t, 15.94-ish. How many degrees of freedom does t have is c. Well, I have a problem with this part of the question. We don't have the data, and I don't see anywhere in the book in this problem where it says how many Archaeopteryx bones we looked at. Do you guys remember how many from the previous problems? This doesn't give n, so I think we'd have to go back and look. So if you went back and looked, what you'd find is that n equals 5. So the degrees of freedom then would be minus 2, which is 3. Yeah. Degrees of freedom is 3. What else does C say? Use table C to approximate the p-value. For us, it's not table C, it's table D. This is from the statistics. The statistics test, the AP test. So if I look at my degrees of freedom as 3, I'm looking for a t-value that's 15.94, almost 16. And as I look across, closest I get is almost 13. So what does that tell us about the p-value? It's less than less than 0.0005. So certainly significant at any alpha. Write a sentence to describe your conclusion about the slope and the true regression line. Well, what they do give us in here is that the null hypothesis is that beta equals 0, and the alternative is that beta is greater than 0, meaning it has a positive slope. So D. How would we interpret this p-value against this null and alternative? Would we reject the null or fail to reject at that p-value? Reject. Oh, good. I thought I saw your mouth fail, and I'm like, wait, no, that's not what I expected. Yeah, we reject the null. We have significant evidence. At any reasonable alpha, because we didn't set alpha, to reject the null and conclude that there is a positive relationship between the femur and the humerus measurements. Okay. So the next question, E, says, calculate a 90. This one covers everything. Calculate a 99% confidence interval. See what with 99% confidence where we think the true slope is. So the formula for this was in day 1 notes, but I think this is maybe the first time we've actually used it. It's the slope, b, plus or minus t star, times the standard error of b. Now, we have the b and we have the standard error of b. That was given to us. All we have to figure out is the t star for 99%. And it's been a while since we've done that. So it's not any of the t values that we've run across in the past. So what we do is we go to our table and we look at the bottom and we find 99%, and then we follow that up until we get to 3, because that was our degrees of freedom, and I find that that is 5.841 is the t value. So at this point we just throw the calculation together. The slope, b, is 1.1969 plus or minus the 5.841 times the standard error of b, which was given as 0.0751. It's handy when that's given because that's kind of a pain in the neck to calculate. So let's see what our calculators say about that. always like to start with the minus myself. So I get 0.758 about 2. Change that to a plus. 1.64. So how do we answer a confidence interval question? We are 99% confident the true slope of the, we are 99% confident the true slope of the line of regression comparing the humerus and the femur, or the femur and the humerus, is between 0.758 and 1.64. This point in the game, there certainly were some shortcuts in this. They made some calculations for us. But what if we just had the data? What if we had to do all that on our own? Come up with all these guys and stuff. We could do it, right? Well, if you want to follow along with me, and I would recommend it, let's go in and find, if you look back at 15.1, we have the data for this. I think I have it in this calculator. Let me look real quick. Yeah. So if you change your L1 and your L2 to the measurements that for these bones, we've got 38, 56, and 59, and 64, 74, and so forth. If you put that in, I'll show you the shortcut to all of this. Alright, so if you've got that, let's go. So let me back up a second. There have been a couple of things, like I've said over the year, when in doubt, standardize, right? For the second semester, I'm going to add another when in doubt. When in doubt, go test shopping. Did anybody go test shopping for this at all? Did you find anything? No? No? Okay. So, we're going to go over to tests. And at the very bottom of our tests, we have line reg t-test and line reg t-interval. I don't know why they're separate from all the other tests and intervals, but they are. So let's look at the test first. It only gives you the option to do this if you have the data. So L1 and L2, yep. Frequency, 1 should automatically be in there. In this particular test, we said that that we were greater than 0, that the slope was positive, it was greater than 0. The regression equation, you can do the vars, y-vars, and all that, and have it graph the regression equation, just like you would with the other, but I don't know that I need that. Calculate. So here we have all the information we need. The t, 15.94, which we calculated. The p-value, we weren't able to calculate that directly, but we used the table to find a number. That is definitely less than 0.0005. Degrees of freedom, our y-intercept, our slope, the standard deviation, r squared, r, it gives pretty much everything you need on there. And the same thing's true if you do the line reg t interval. Frequency, it says 1, leave it at that. Confidence interval, 99%. That's what it asked for. Calculate. There is our 0.758, our 1.64. And all the other stuff that the other thing calculated. So, use the tool. Use the tool. All right.